Good morning, everyone. I am Mohamed Rhouma. I'm a PhD student at CESBIO. I started my PhD at January. It's only 6 months. My supervisors are Lionel Jarnon and Sylvia Valero. And today, I will present my PhD work, my PhD subject, artificial intelligence and physical modeling for water needs mapping in semi-arid environments. To start with, my goal of PhD is to estimate the evapotranspiration. The evapotranspiration combine two processes, the evaporation and the transpiration. The evaporation is the direct water loss from soil and water surface, and the transpiration is water loss through plant leaves and stem. Why the evapotranspiration is important? Because it is a key indicator for crop water needs and irrigation planning. And also it is important to understand water balance in ecosystems. The evapotranspiration is a variable in time and space, and also it depends on several factors. The evapotranspiration requires several parameters to be estimated. For example, the meteorological variables, which is the air temperature, for example, net radiation, precipitation, wind speed, and so on. And also the remote sensing products like leaf area index, FAPAR, FCover, soil moisture, and so on. We actually now experience a revolution in satellite data availability for Earth observation. So we have massive data archives. We have decades of satellite observation from multiple sensors. For example, for Landsat, we have over 15 years of continuous Earth observations, and also we have MODIS, Sentinel, etc. So with this wealth of satellite data spanning very long periods, it is effective to explore and use this data to estimate the evapotranspiration. But with the remote sensing, we have several challenges, like we have spatial resolution and consistency in input dataset, temporal resolution limitations, and uncertainty of input data models, and also we have problems with physical model. For the first challenge, spatial resolution and consistency in input dataset. The evapotranspiration estimation requires multiple input data from different sensors, but each dataset has a different resolution. For example, for the NDVI from Landsat 8, we can calculate it using 30-meter resolution. But if we use LI from MODIS, we have 500-meter resolution. So we cannot directly combine those datasets with different resolution. So also, if we do a sampling technique, this will introduce some errors and uncertainty. For the second challenge, temporal resolution limitation, as we know that evapotranspiration is a dynamic process that varies throughout the day and season. But for satellite, we have a limited revisit frequency. For example, for Landsat 8 or 9, we have 60-day repeat cycle. For Sentinel 2, we have 5-day repeat. So why this is critical? Because evapotranspiration changes rapidly due to the weather and irrigation and plant growth. With this, we will miss important events. For this third challenge, which is the uncertainty of input data models estimated from remote sensing, that the data products that we can get from satellite measurement like LAI, FAPAR, FCover, can have several uncertainty. For example, the source of uncertainty that can come from, for example, the model assumption. The retrieval algorithms of this vegetation indices can use simplified assumptions. So this will impact the estimation of evapotranspirations and can we have some errors. Also, for the challenge 4, physical model limitation. To estimate evapotranspiration, we can use several physics-based model. But with this model, we have several issues. For example, in the input dataset, we can have difficult parameter to estimate and hard to get. Also, the physical model can simplify the reality, and also they do not perform well at extreme conditions. So our objective, we aim to develop a model to estimate the evapotranspiration and address this limitation. Our target is to estimate, to probabilistically estimate the evapotranspiration with high spatial resolution and high temporal resolutions. And also, it can support the new Trishna mission. So for our AI application in our system, we can use AI to improve our input data, to enhance the resolution of our AI and canopy temperature, and we enhance the estimation of those parameters. And also we can use AI to integrate diverse remote sensing and ground truth ground data, and also to use AI to estimate difficult parameters like air conductivity and stomatal conductivity. This is our approach. We have first the input data, input features like leaf area and X, precipitation, soil moisture, that we try to enhance and estimate. We can use these parameters, we can input these parameters to our AI model, and the AI model, it will output the physical parameters that difficult to get or difficult to estimate, like aerodynamic resistance, stomatal conductivity. We can use these parameters and input it to the ET model, the physical-based model that estimates the evapotranspiration, and finally, we get the evapotranspiration. So in the last few months, I start collecting data that we may use to build our model. We have different sources of data, the actual evapotranspiration, the vegetation indices, and the remote sensing products, and also meteorological data. For the actual evapotranspiration measurement, we use it FluxNet. FluxNet, it's a global network of energy flux measurements. It does provide ground truth ET measurements and also provide meteorological data like precipitation, temperature, wind speed, etc. Why FluxNet is valuable? Because it does provide a long-term continuous ETE measurements and quality control data. For vegetation indices that we may need for evapotranspiration, we concentrated our work to estimate the critical one, like the leaf area index, FAPAR, and FCover. So for that, we used a model called PROSAILVAE, which is developed by an old PhD student, UL Zara. We trained PROSAILVAE using Landsat 7 and Landsat data. PROSAILVAE, it's auto-variational autoencoder that decomposes into parts, the encoder parts and the decoder parts. The encoder parts is simply a neural network that take the original surface reflectance and provide us by a distribution of the parameters of the decoder. The decoder that we use here, it's a physical model that takes some parameters like LAE, water content, and etc., and does simulate the reflectance, the surface reflectance. So the encoder take the original reflectance. We provide us by a distribution of the parameters of the PROSAIL in the latent space, and PROSAIL take these parameters or this distribution and provide us by the simulated reflectance. We have two losses here, the reconstruction loss, which measure the reconstruction image, the similarity between the reconstruction image and the original image, and we have also the KL diversion loss, which add the constraint into the latent space, into the parameters of the latent space, into prior into defined prior distribution. And also we did several validations of the ground truth of the LAI and FAPAR and FCover with different state-of-art model like BVNet and OpenET. BVNet, it's a neural network that is trained in PROSAIL simulation that estimates the LAI and FAPAR and FCover. OpenET, it's a random forest model which is trained on Landsat 8 data and Moody's LAI. For PROSAILVAE, we validate our data into different sites like Neon, FRM4G, Imagine, and IACOS. Those sites provide us by, or those projects provide us by ground truth LAI, FAPAR, and FCover. For the LAI, we can see that we have better results with the PROSAILVAE. For FAPAR, we have similar result, and also with FCover. For the conclusion, as we know that evapotranspiration faces several challenges with the remote sensing data, so our objective basically is to build an hybrid model that address these issues. We are still in the data collection phase. We are still in the data collection phase using FlexNet, and we try to enhance the PROSAILVAE estimation. And that's it. Thank you.
All right. Thank you, Hadi. We have